Hi guys, this is Mr. Adams from Midway High School, and this is a video on collision theory. Now, in the collision theory discussed in class, right, that if you're able, right, to increase the frequency of collisions, okay, you will also be able to increase the chance of effective collisions, right? And if you increase the chance of effective collisions, the reaction rate of the reaction will also increase, okay? Now, what's an effective collision? An effective collision is one where you have the right amount of energy or force and you have the proper angle or orientation when the reactants are colliding with each other. You must have both of these guys. You cannot have just the right amount of force without the proper angle, or you can't have the proper angle without the right amount of force. We also agreed in class, folks, that there are a certain number of factors that affect the rate of reaction. And a number of these are common sense, right? Like, for example, temperature, okay, concentration, surface area, pressure for gases, right, catalyst, and ionic versus covalent. We tended to agree that ionic reactions in general react faster than covalent. There's a little controversy about that, but that's the situation. Okay. Now, for our demo, right, our simple demo, we have water here in ice, and if you can see that LT means lower temperature, and over here I have basically room temperature water, the higher temperature. Okay, so we're going to compare temperatures there. We also are going to have acid, right? One of lower concentration and one of higher concentration. I diluted this one much more. Okay, so this one's lower concentration. And over here, guys, I have, we're going to test surface areas. This one's going to have a lower surface area, and this one's going to have a higher surface area. So we're going to test those in a second. Okay. All right, guys, I'm back. We have our lower temperature water, which I just took out of the ice bath, and we have our room temperature, higher temperature water right here. Now, what we're going to do, I'm going to take some of these guys right here, okay, I'm going to drop them in. I'm working with one hand, so let me see. Okay, this is the lower temperature, one, and it's the higher temperature. I'm going to see if we see any difference, folks, in the evolving of bubbles, okay? All right, so if you notice this guy right here at higher temperature, okay, is bubbling a bit more than this one right here. So this one's bubbling also. The lower temperature one, LT, is bubbling, but not as rapidly as this one right here. You guys see that? Okay, this HD, higher temperature. Okay, and this one is the lower temperature one, not bubbling as fast. Okay, so why did that happen? Let's explain that. All right, guys, so going back to the collision theory, right? All we did when we had the higher temperature, I see the bubbles right there compared to this one. Okay, we are increasing what? The average kinetic energy, which is the definition of temperature, right? The particles have a greater chance of moving around. They move around even more rapidly. They have a more chance of bumping into each other. It's increasing the frequency of collisions, okay? And remember, when you increase the frequency of collisions, you also increase the chance of the effective collisions, right? And when you increase the chance of effective collisions, your reaction rate will go up. Okay, so once again, that's why this particular higher temperature water right here with a pill in it is much more rapid than this guy with a lower temperature. Okay, cool. All right, folks, back again. Now we have our low concentration acid, right? Hydrochloric acid at low concentration, more dilute. And we have our higher concentration HC acid in this container over here to the right. Now what I'm going to do again, once again, I'm going to drop the pills in and let's see if we can see any type of significant difference, all right? Now technically I'm supposed to drop them in simultaneously, but since I'm working with one hand, no problem, here we go. Hopefully the half a second difference doesn't make a big deal. Okay, alrighty, we drop those guys in. Okay, let's see what happens. We're looking at low temperature over here, and we're looking at the higher temperature over here. Oh goodness, concentration. Okay, so once again, guys, this is a low concentration versus high concentration. Okay, this is low concentration. This is higher concentration. All right. Now, the higher concentration, if you notice, is a bit more okay, in terms of the amount of bubbles produced. Not much more, okay, but you notice that it's the circumference, everything is all filled already, right? Rather than this one, okay? So this particular experiment, not as conclusive as the temperature, but the higher concentration did produce more bubbles more rapidly, okay, but it wasn't that much more faster, okay. Maybe I should have made a much higher difference in dilution, but it still proves the point. You see, you got more bubbles. If you notice, I'm doing it like this. The height, look at the height of those bubbles versus the height of those, okay. So you saw a significant difference in height. So yeah, you could pretty much say that, you know, the higher concentration definitely is much more rapid. It's evolving more bubbles than the lower concentration acid. Okay, so let's analyze why. Okay, guys, going back again to the collision theory. What are we doing when we have a higher concentration? We have more solid particles with the higher concentration. What does that do for us? Okay, in terms of interaction between the reactants, right? We are increasing the what? The frequency of collisions. Once we do that, what are we increasing again? The chance of effective collisions, right? And when we increase the chance of effective collisions, we will increase the reaction rate, okay? Notice the higher concentration guy is like, you know, see that height right there versus that height right there? Okay, he's almost coming out. Okay, so yeah. All right, so once again, folks, don't guess and don't mix and match with this topic. Ask yourself, is the factor going to increase the frequency of collisions, or is it going to decrease the frequency of collisions? And from there, you can tell, okay, whether or not your chance of effective collisions will increase and whether your reaction rate will also increase. Okay, cool. Next one. All right, guys, we're going to do surface area. Now, I got 2 pellets left, folks. I got to be careful, right? So one of them I'm going to leave whole, all right? And the other one I'm going to grind in this trusty mortar and pestle right here. So I'm going to crush this guy up, okay? And we agreed in class, folks, that when you cut things up, when you make it smaller into pellets or into powder, you are increasing the surface area, right, guys? Okay, because now you have more smaller particles, and around each smaller particle, its area of its surface exposed to the environment. Okay, and when you expose each one of those small particles, its area is exposed to the environment, guess what it does? It increases your chance and frequency of collisions and the chance of effective collisions, right? So once again, smaller particles give a higher surface area. Now what we're going to do, we're going to place this into the water and see what happens. Okay, we'll do it in a second. All right, guys, I have 2 containers of water right here. One of which we're going to try the low surface area guy, the whole pill in. And the other one is going to be the ground up high surface area pill, okay? So what we're going to do, we're going to put both of them. The temperatures are the same. There's no acid in them. So both of them have the same temperature, water, pure water, no problem. So what I'm going to do first, I am going to drop this guy in, okay, first, and then I'm going to try and do this one a little quickly right after, okay? But once again, I should have been doing this simultaneously for the purposes of, you know, of accuracy in the experiment. No problem. Okay, 1, 2, 3, bam, and I'm going to sprinkle that guy in there, bam. Okay, let's see. Okay, we're looking at both of them, trying to look at both of them simultaneously. We see gas being evolved in the low surface area one. We also see gas being evolved in the higher surface area one. Now let's look at the amount of bubbles. The amount of bubbles for the low surface area guy, the whole pill, is there, okay? It's not much because you can see the pill still floating there, right? And over here, guys, you notice, right, the height of the gas particles are a bit higher, definitely, right? So definitely the higher surface area guy is reacting faster than the lower surface area guy, the lumpier, larger guy, right? Now, once again, folks, it's all about, since the particles, there's much more individual particles in their area the surface of the area is exposed to the environment, there's much more chance of effective collisions due to the frequency of collision being increased. Okay, there's much more particles colliding around and all over the place, and there's much more chance of collisions, right? So it's all about frequency of collisions and increasing the chance of effective collisions, people. Okay, once you're able to increase the chance of effective collisions, all right, your reaction rate will go up. And how do you increase the chance of effective collisions? By increasing the what? The frequency of collisions. So once again, guys, hopefully these three make sense. I want to do one more catalyst in a second, but hopefully these guys make sense. So this was temperature over here, all right? The higher temperature one. This one was concentration. We agreed that the higher concentration guy won, that maybe I should have did a little more difference in the dilution, but still show the effect. And this guy right here, we saw that the higher surface area guy initially won. Okay, so yeah, alrighty. All right, guys, back. Now here we have some hydrogen peroxide, right? Just ran to Walgreens and got some hydrogen peroxide. Like you'd always have in your medicine cabinet. Now this is only 3%. Typically I like to use 30%, but you know, this should be pretty good. Now this 3%, we could use it for like, you know, cuts and bruises and so on to kill, you know, germs. And what I'm gonna do, I'm gonna put some of this inside of the this test tube right here, okay? Now what's gonna happen is this. You're not gonna see any type of reaction or anything, but what we have, folks, we have this guy right here. This is potassium iodide, Ki. Okay, I don't know if you could see that or not. All right, it's a white crystalline ionic compound, Ki. Okay, no problem. So I'm gonna put some inside of the peroxide, and we'll see what happens from there. I also have some dishwashing liquid, which is going to help me see the bubbles that get evolved. Because what's going to happen, people, this guy right here, hydrogen peroxide, right, is breaking down, decomposing very, very slowly into water and oxygen. But the soap is going to help us see that the oxygen gas is being given off as it gets trapped in the bubble. So hopefully we see the effect using hydrogen peroxide, our catalyst potassium iodide, and our soap. Okay, cool. Back in a sec. All right, guys, I just put some peroxide, this peroxide right here in this test tube. Now, if you notice, right, it's pretty, you know, normal, nothing, not doing anything much. Okay, just there, right? But it's decomposing very, very slowly into water and oxygen, right? Okay, but honestly, you can't really see nothing with the naked eye right now. So what we're gonna do, we're gonna add a catalyst to it and see what happens. Now, as I said before, guys, what we're gonna do, we're gonna add a little bit of soap. Okay, so let me pop some in there, just a tad. All right, should be good. Okay. So the soap is going to help us see when the oxygen bubbles are escaping, okay? Because pretty much when it's not there, you don't really get to see that nice effect, right? Okay, so there you got our little dish soap in our peroxide. Bam. Okay. Alrighty. Now I have a tiny amount of potassium iodide that I diluted, made it aqueous. Okay. And what I'm going to do now, I'm going to drop it into this peroxide with a small amount of soap in it. Let's see if we can see the effects. I'm just trying to mix it up a little more. Okay, make it a little more uniform. Okay, let's see what happens. Alrighty. Okay, hold it over here. Okay, let's see. I see bubbles evolving slowly. Okay. Now, if you notice at the bottom, I don't know if you guys can see or not, Okay, it's getting a bit more yellow. Okay, from the original color that it was. Now, if you notice, do you see any bubbles forming there in the, right here? Bubbles in formation. See all that right there is bubbling up? That's all oxygen being given off, being involved, okay? So you can see the reaction occurring much, much more rapidly than when it was before when I showed you guys, right? Now, normally I like to use 30% peroxide with potassium iodide because you get a much more dramatic effect. The bubbles evolve much more rapidly, and the foam actually shoots out a test tube or this graduate cylinder. But no problem. This smaller scale still shows the fact that we're having oxygen gas being evolved. The hydrogen peroxide is being decomposed much more faster due to the presence of catalyst, okay? And we talked about this in class. How does a catalyst work? It lowers the activation energy hill. So the reactants get to the product side faster. Products are able to go to the reactant side faster. So it lowers the hill, creating an alternate pathway, okay, an easier pathway for the reversible reaction to take place. See, that's still moving up right there. Okay, pretty cool. All right, let's leave it a bit more and see how far it goes. Okay, still bubbling, still bubbling. Okay, so you guys see that? Still bubbling right here. It's going up there. So you see all that foam right there is oxygen trapped inside the dishwasher liquid. Okay, so once again, what are the factors that affect our rates of reactions? Temperature, concentration, surface area, pressure for gas, and catalyst. Also ionic versus covalent. Ionic beats covalent. Okay, alrighty. So here we go, folks. So pressure, we can talk about in a second. All right, folks. Now for pressure, we're going to use our imagination, okay? Because, you know, I don't have any gases that, or gas and other substances that are going to react nicely, okay? No problem. But we'll use our imagination. Here we have part of a syringe, right? And I have the plunger right here. So I'm going to put it in, bam, all right? Now, notice I have this much volume, yes? Now we're going to imagine simply, guys, that inside of this cylinder part right here, it's we have gas reactants, yeah? Now, as I press on the syringe, people, okay? Oh, goodness. There you go. I'm pressing. Now, can you see this black part right here? Alrighty. What's happening to the volume as I increase the pressure, people? We notice that the volume decreases, right? Now, once again, the same amount of particles are still in the cylinder, but they have less volume. So guess what's going to happen? There's going to be more frequency of collisions because there's less space to move around, okay? As I said before, if you take 50 people from a large room and put them in an elevator, there's much more squashed and much more collisions, right? And when you have more collisions, more frequency collisions, you're going to increase the chance of what? Of effective collisions. And when you increase the chance of effective collisions, your reaction rate goes up. So this is essentially how pressure works, folks, okay? Now, once again, I want to make one more point. In terms of pressure, right, you can also say volume is a factor too, right? But volume and pressure go hand in hand. Remember Boyle's law? As you increase the pressure at constant temperature, the volume decreases. Well, it's the same kind of concept. If you increase the pressure, it's basically the same as decreasing the volume. Okay, guys? So, as always, hard work plus sacrifice equals success. Review these topics and not that bad. Be well.